Hello everyone. In this video we will begin to examine topic 5.2, the heating effect of electric currents, and in fact we will begin to discuss resistance. So in the previous video, in the previous couple of videos, we discussed two of the most important concepts for electric circuits. We've discussed the idea of electric potential difference and the EMF as the energy per unit charge, either generated in the battery or delivered to a resistor or to a lamp. And we've discussed the idea of current. Which brings us to our next question. What is the relationship between the potential difference across a circuit element and the current through it? The answer is, it depends. Fundamentally, it depends on what that circuit element is. But we have a word for that relationship, and in particular for the ratio. We call sort of the relationship between the applied potential difference to a circuit element and the current that ends up going through it the resistance. So we formally define the resistance of a circuit element as the ratio between the potential difference across the circuit element to the current through it. So it's formally defined like this. R is defined to be some delta V potential difference divided by the current. Resistance has its own unit, known as the ohm, written like this, named after Georg Ohm, and uses this capital omega for its symbol. 1 ohm is, as you can see from the definition, 1 volt per amp. Okay, so ohm is a derived unit. It's a volt per amp. And this is a definition. So it's really important to recognize that as a definition, the resistance is equal to delta V over I. This is never false. Okay, this is never false. And I'm going to note right here, although we'll discuss it in great detail later, but the relationship is always true and is often confused with Ohm's law, if you've seen Ohm's law before. And Ohm's law is not always true, and we'll sort of have to pull those apart as we move forward. And the general idea here is that for a given circuit element, if you crank up the potential difference, but you get the same current out, so let's say delta V goes up, but you're only getting the same current out, then that element is sort of resisting that current more. You can think of the resistance as like the property of the circuit element by which it resists current going through it. Objects with a high resistance end up having low current for the same potential difference. Objects with a low resistance will have high current for the same potential difference. A resistor is an object, a circuit element, with a fixed resistance. In the IB and in other sort of international structures, you will see it drawn like this, sort of a bare rectangle. That's what is known as a resistor, as an element in a circuit. There are objects that have fixed resistance that aren't resistors, but in general, sort of, we will deal a lot with bare resistors, so objects with a fixed resistance. The American standard, and you'll see this in certain resources, is to draw a resistor just with a jagged line like this. So that's the symbol. You'll see that occasionally, I'm sure. All right, so although R is defined to be delta V over I, this relationship between delta V, I, and R, I would strongly encourage you to sort of memorize or use rearranged like this. And the reason is effectively for the same reason as we'll see as in Newton's law, which is that delta V for any given circuit element can be understood as sort of the push. It's the energy per unit charge given to the charges. If that number is higher, then more energy per unit charge is given to those charges. And the resistance is sort of a property of the element. Although it's defined to be delta V over I, what what gives an object its resistance is due to sort of its microscopic properties. It's how much that particular bit of material resists the push being given. And the combination of them, that outcome, is current, the rate of charge flow. So if delta V is your push, R is your resistance, the outcome is the current, the rate of charge flow. This is sort of the motion that happens as a result of this push and this resistance. And if that sounds familiar, that is exactly like Newton's second law, arranged like this. So the net force comes from sort of external objects or external things, sort of applying forces to a single object. The mass is its resistance to being accelerated, which are both properties of the object itself, and then the acceleration is the resultant effect. It's the outcome of the combination of the net force applied to the object from the outside and the inertial mass, that property of the object that resists these forces. This is exactly the same with current, potential difference, and resistance. And the way we describe it is we say, okay, the potential difference, delta V, is applied to a resistor with resistance R, driving the current I through the resistor. So if we look at this simple circuit here, we've got an EMF of 3 volts. It's driving a current through this resistor. The resistance is given as 2 ohms, and so the resultant current can be found by observing that if the EMF of the battery is 3 volts, then the potential difference across this single resistor here is also going to be 3 volts. And 3 volts across the resistor divided by 2 ohms, the resistance of the resistor, gives a current through the circuit, both leaving the battery and through the circuit element, the resistor in this case, of 1.5 amps. This is sort of a classic example of using this equation. We're going to use it over and over and over, and it can be used in other orientations too. So if you don't know the resistance, you can find the resistance from the current and the potential difference, and you can find an unknown potential difference from a current and a resistance as well. And I'd encourage you to do so here.